Now let us see what are the different aspects which will decide the rate of SN1 reaction, reactivity of SN1 reactions. Okay, how does the different factors affect the rate of SN1 reaction? Number one, nature of the alkyl group. Factors affecting oh, it is very slow. Wait 1 second. Let me change. Let me see whether which connection I have got now. Okay, it is best. The one which I have got is quite good. Supposed to be good connection. Okay, let us see. Affecting factors affecting the reactivity very slow of SN1 reaction. Okay, let me see whether I can take like zero. And just wait for a few minutes. By the time this will be over. Wait a minute. If I am getting that other board, probably that will be faster. Let's see. I don't know whether that will work. Let me see. One sec. So നിങ്ങൾക്ക് ബോർഡ് കാണുന്നുണ്ടോ? ഹലോ, ഇപ്പൊ പഴയതാണോ ഇപ്പൊ പുതിയതാണോ? ഇപ്പൊ ഞാൻ എഴുതുന്നൊക്കെ കാണുന്നുണ്ടോ? 26th July. ഓക്കെ 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 ശരി. ഇത് കുറച്ചും കൂടി പാസ്റ്റാ. ഒരു മിനിറ്റ്. Okay, now the factors which are affecting the nature of the SN1 reaction. First one, nature of alkyl group. Nature of alkyl group. Now, SN1 reactions. This is SN1 reaction. You have a nucleophile, You have the nucleophile. Now you will get the carbocation first plus Cl minus. Now the one which is having a strong, a stable carbocation, the substrate which forms a stable carbocation, that will be such substrates will be favored in SN1 reaction. That means tertiary faster than secondary, faster than primary. So primary undergo SN1 reaction very rarely. Practically it does not undergo SN1 reaction. Similarly, if you have vinyl allyl cation, CH2 plus, then benzyl carbocation. Okay, these two will come actually here. That is, they are slightly less reactive than secondary, or yeah, and then primary. So you can say tertiary, secondary, there is no much difference, but still allylic, same as benzylic, and then primary. So this is the order. Clear? Primary. The primary can be C2H5, and last you have methyl group. Methyl. So that is the order by which this one reacts. And you know what is the reason for that? The reason? What's the reason? Stability of carbocation. Stability of carbocation. Now when you are asked in the exam, don't simply write this. Now what you have to do is you have to stabilize this one. Show the stability of this. For example, this. How we do? What are the methods of stabilization? Number one, we have described this before. Number one, by inductive effect. Don't write English. Then you will ask me, sir, what are you writing now? Inductive effect is, you cannot see in an English dictionary. It's not English. You know that? Okay? So that's a language of chemistry. Now see here. How will you describe? This is what you have to write. This is enough. You don't have to write anything else. Just write these full structures. See here. You are writing too many paragraphs, which I find it very difficult to read. Unnecessary paragraph. See, put the arrow like this. This is the inductive effect. Put arrows. See here. Very clearly tells you. Any examiner will know what is whether the student knows the answer. See this. Now you just write the word stabilizes. Stabilizes. Over. Now number two. What is the second? Hyperconjugation. Again, not English. It's also chemistry. You take a dictionary, you will not find this word. Got it? That's the meaning when I tell you, don't write English, write chemistry. Now, how will you explain the hyperconjugation? Simple. Draw the structures. None of your chemistry, your paper is containing a lot of English. Oh, one second. Where is my, yeah, right there? Yes. Now, see this, C plus. You write this C, H, CH3, CH3, CH2. Just put an arrow here, okay? And you can put a sort of resonance structure symbol. Nothing wrong in it. Double bond, CH2 plus, oh sorry, plus is not there. Plus is not there. Plus has to be back. One sec. Yeah, plus should be on the H. And now you write CH3. CH3. Right here. How many structures? Total 10 structures possible. Got it? See that? This is enough for the answer. For stability of carbocation. This is how you have to answer. Don't write too much of English. Minimum English is required. Okay, now let us look at the second factor. Number 2, nature of leaving group. Nature of leaving group. Now tell me, look carefully. This is your substrate. This is your leaving group. And this is your this mechanism. Okay. Now, if this reaction has to be faster, this should be a very good leaving group. So, leaving group should be a very good leaving group. A poor leaving group, a very good leaving group. Now the question is, what is a good leaving group? What is a good leaving group? Oh my God, my board will stop now. That's a problem with this one. Okay, what is a good leaving group? It is a good leaving group is the one which can be stabilized, which is stabilized after leaving, after the bond is broken. Okay, but the bond, after the bond with the substrate is broken, it has to be stabilized. For example, look here, you have a leaving group like this. This is one of the best leaving groups possible. Oh, sorry. This leaving group is called tosyl group. Tosyl. Okay, or in short, it is written OTS. This is a short form. So OTS is a very good leaving group. Can you see the board? I hope you can see the board, right? Yeah. Now, OTS, if you're not able to see the board, you have to tell me. Huh? Now, OTS is a very good leaving group. Why? Why? Because once the OTS is coming out of this reaction, for example, suppose I do a reaction like this with OTS. This is my starting material. I react with this nucleophile. Okay, I will get in the first step, I get the carbocation plus my OTS O minus S double bond O, double bond O, and phenyl ring with a methyl group. Now see, this I can delocalize this charge. I can write 3 resonance structures for this. 3 resonance structures. So this is a very good leaving group. This is a very good leaving group. Similarly, a leaving group which will form a stable molecule. For example, suppose I have a leaving group OH. OH is a bad leaving group. OH is a bad leaving group. But if you put a little acid into this, what will happen? See here. This will react. It will get protonated. See very clearly what we have done. CH plus. Now it has become a good leaving group. The nucleophile can very easily attack here. See, it can attack here. So that's a very good leaving group, right? Now see another one. Let me see from whether I remember something. Let me see. Think about the different. If I think about another leaving group like this, see here. Suppose I got a benzene ring. I got a benzene ring here, and then suppose I got an N triple bond N group. Okay, this is a very good leaving group. Very, very good leaving group. There's a positive charge. This is benzene diazonium chloride. Why? Because, see here, what you're going to get is a plus charge here and nitrogen molecule, a very stable compound. Stable compound. Okay, so this is how you decide the nature of the leaving group. So how do you decide the nature? Number one, a stable neutral molecule is formed. A stable neutral molecule is formed. What is the second aspect? Stabilized after leaving. Stabilized after leaving the molecule. What are the examples for this? Here it is H2O, NQ. Here, what is example? OTS. It's a very good example. Okay. Similarly, Cl minus is a good leaving group. Cl minus is a very good leaving group. It will be solvated, right? So if you take the order of leaving group ability, in the case of leaving group ability, if you take halogens, I minus is a very good leaving group. Br minus, Cl minus, and F minus. Okay. Well, but only problem is when you this is only when you consider the nature of the leaving group. But when you in the practical aspect in the industry, if you are doing this experiment, what is important is not only the prime concern is cost. Okay, making the I minus a good leaving group, it's a good leaving group, but the cost of iodo compounds are very high. The cheapest halogen compounds are chlorine. cheap. But they are not relatively, they are bad leaving group. So many a times, wherever possible, we use bromide because it is intermediate, less costly, but more costly than Cl. So wherever possible, we will go for Cl minus Cl. Otherwise, we go for Br bromo compounds. Okay, so that way you can consider. You can say Ri alkyl iodides react faster. Reactivity Ri react faster than Rbr, faster than RCl, faster than Rf. So that is the nature of leaving group. Now let us look at the nature of nucleophile. How does the nucleophile affects the rate of SN1 reaction? How does the nucleophile affect the rate of SN1 reaction? Okay, in the case of SN1 reaction, weak nucleophiles will undergo SN1 reaction. What are the weak nucleophiles? Yeah, this was a question. H2O is a weak nucleophile. Then NH3 is a weak nucleophile. RNH2 is a weak nucleophile. RNH2. Okay, these are neutral nucleophiles. So neutral nucleophiles are weak. Neutral nucleophiles are weak and they undergo SN1 mechanism. The reactions involving these reagents, it follow SN1 mechanism. Okay, but if you have strong nucleophile, we have already discussed that strong nucleophile will prefer SN2 mechanism. Okay, so these are the SN1 and SN2 mechanisms. You can make comparison of SN1 and SN2. Comparison of SN1 and SN2 mechanism. You can write all these points. You can make a table on different aspects. How can you compare? You can compare on kinetics. You can compare on stereochemistry. You can compare on mechanism. You can compare on energy profile diagram. Do one thing. You prepare a table for this without looking at the textbook. And then you can compare nature of leaving group, nature of substrate. What type of substrate for each one of them. Nature of nucleophile. Okay, nature of leaving group. Nature of leaving group. And then solvent also, but there is no description of the solvent. It's okay. So these are the aspects of different two types of SN1 and SN2 reactions. Okay. Now we have to take some other reactions. Number one, Wood's reaction. Wood's reaction. You must be knowing, you must have heard this word in your +2. Okay, what is Wood's reaction? Wood's reaction, alkyl halides. Oh. alkyl halides are X, sorry, are X plus sodium, okay, plus XR. That will give you alkanes.